This year, Friends of Now has hosted 2 talks on quantum information science and quantum materials, which is appropriate because the United Nations declared 2025 to be the International Year of Quantum Science and Technology. But today, we are going to hear about something more familiar to the public, buildings, an area of research that the lab has done a tremendous amount. We will also be hearing about energy, computer modeling, and artificial intelligence and digital twins. I am pleased to introduce Joshua New, our speaker today, who will give a lecture titled An Energy Model of Every U.S. Building, Science and Business Uses. Dr. New, a native of Alabama, is a distinguished scientist in the Grid Interactive Controls Group in the Electrification and Energy Infrastructure Division of Oak Ridge National Laboratory. In 2024, he received the International R&D 100 Researcher of the Year Award. And that's how I, as a former board member, learned about him, because I read the ORNL news releases on the lab website, which is ornl.gov. In 2016, he won an R&D 100 award titled Proof Savings Calculator Suite. R&D awards are often called Oscars of Invention. Dr. New is also a joint faculty member in the Electrical Engineering and Computer Science Department and Bredesen Center at the University of Tennessee at Knoxville. And that's where he received the Outstanding Mentor Award in 2024 and his PhD in Computer Science in 2009. He has more than 200 peer-reviewed publications. He managed research portfolios for the Building Technologies Office of the U.S. Department of Energy that totaled more than $25 million while he was on loan to DOE. Over the past 15 years, he led more than 225 projects totaling $350 million. Please join me in welcoming today's speaker, Joshua New.
For that kind of introduction, Carolyn. And yes, I am a native of Alabama. We talk a little slower down there, but we try to speed it up a little bit in the presentations. If we can swap over to the presentation, and I will go through the table of contents, kind of what I'll talk about in this presentation. I'll try to keep us on target, 53 minutes of presentation and 15 minutes of Q&A after. So the presentation talk is an energy model of every U.S. building, science and business uses. So I'm going to spend a little bit of time talking about the context, the background, the infrastructure of the lab, how we work with it, who I am. Then I'll talk about 20% of the talk on the science and how we achieved the things that we achieved. And then most of the time, I'm actually going to talk about how businesses and industry is using this and maybe some thoughts toward the future. So I'll talk a little bit about myself, if you'll forgive me. I'll talk a little bit about DOE and ORNL's role in some of DOE's missions. I'll talk about the spoiler alert of how we created an energy model of every single U.S. building, the software suite that we developed to do that, and then how we're creating future weather files to see how that will impact our buildings in the future. Then I'll spend most of the time probably talking about how businesses are actually using this in the past 5 years. So a little bit about me. This is the little boy of Joshua New. And my grandfather here is teaching me how to read from the morning newspaper. My grandfather was an amazing guy. He was initially in the Navy, but he sleptwalked and didn't know how to swim. So they put him in the Air Force. And he was actually stationed at Oak Ridge National Laboratory when they were building it. His job was to go around and make sure that people were where they were supposed to be. And he ended up realizing he could talk to the foreman and figure out where everybody was, so he could do a full day's job in about 3 hours. After they built Oak Ridge National Lab, he was when he was stationed at Oak Ridge National Lab, he was told that if he was asked where he worked, he was supposed to say he worked at a bubble gum factory, which I always found was interesting. And then afterward, he was actually stationed in occupation Japan. He still, to his dying day, could recall the like 25 cities from the train schedule in Japan. Just amazing. This is me in high school. I like this picture because it's like the books are permanent and we're just the ATCGs floating through space and time, ephemeral entities that we are. This is me at the University of Tennessee defending my PhD dissertation. So I was always very focused on education and personal growth. This is the R&D 100 roof savings calculator, which I got with Bill Miller. So I graduated UT in 2009 and I applied for jobs everywhere. I submitted over 200 job applications to Oak Ridge National Lab alone, and I was getting rejections for 3 years after I had been hired. But Bill Miller is the one that basically got me on at Oak Ridge National Laboratory. And this is the reason I do what I do, creating a future for my 4 little kiddos, ages 8 to 13. In my spare time, I'm an avid reader. I believe in lifelong learning. So I've traditionally read over 50 books a year, so a book a week for a little over a decade now. I'm an avid PC gamer, so I'm getting old. I'm not as quick as I used to be. But back in my college days, I was in the top 10 of the world and playing a first-person shooter game called Team Fortress Classic. And you had to play at least 14 hours a day to be competitive at that game. And then I've been playing volleyball since I was 4 years old. It's the only physical activity I get that keeps me in shape. And I don't know if you guys have realized this, but as you get older, you lose muscle mass for no reason. So it's like you got to work really hard to jump as high as these 6 foot, 20-year-old, hot shots. But I've met a lot of friends through local Oak Ridge, Farragut, and Knoxville Parks and Rec League volleyball. I have a lot of good friends there. I've been working at the lab since 2009. I've been joint faculty at the University of Tennessee since 2012. I was on loan to the Department of Energy. In 2020 to 2021, I was an M&O contractor, which, interesting note, Oak Ridge National Laboratory is an M&O contractor to DOE. So I was like a national lab. That was DOE. And then I was also founder and CEO of a startup company and software that licensed technology from the laboratory and tried to commercialize it, and did so fairly successfully and ended up selling the company in 2020. So just like in life, like the best way is just to do a deep dive into it. And, from startup company to federal contractor to university to federal government, all different boats that move at different speeds. There's different trade-offs. And it's interesting, the complexity of the environment in which we can work. So this is a summary of me. I hold several certifications. I had a good friend. I think we all need good friends to challenge us occasionally. So we had a challenge to put more letters after our name than in our name. So I got several certifications and to make sure I know what I'm talking about. Certified energy manager, which deals with the working physics and fluids and equipment to calculate that correctly. Measurement and verification professional, which is an international protocol that says when you build a model of something and you compare it to real data, how good does it have to be to match to be investment grade? There's international protocols for that in buildings. Project management professional, I manage a lot of projects, usually about 10 a year, and making sure things are on track, on schedule, on budget. There's clear metrics and processes for that. A lot of people kind of discover that, but it's good to know how that works. And then I developed a lot of software, so I'm a certified Scrum Master. I'm also involved in several volunteer societies. The thing that takes most of my time is probably ASHRAE. I'm the chair of ASHRAE Standard Committee 169. They set 24% by page count of the U.S. building codes. So everybody in the nation that builds a building has to do so according to the standards that the committee that I chair sets. That is adopted internationally. I don't have a percent page count. I guess it's about 10%. international building codes as set by that committee. So a lot of people working very hard, as you know, behind the scenes, developing codes and standards and processes that make it into the institutions that permeate the globe. And then this past year, I was honored to be the R&D 100 Researcher of the Year. It's very humbling because I've just kept my head down trying to do what I thought was important work. And then it's good to be recognized every once in a while. Very humbling because there were 10 candidates and participants from over 13 countries. So big thanks to all the people that make this kind of thing happen. It's not that Rome wasn't built in a day. There's lots of societies and awards and work that goes into achieving these awards that you never see all the ice under the iceberg, right? You just see the little tip. And I wanted to say that I dedicate that award to my father. My father passed away a little over a year ago, and he was an educator and a really good man. He always instilled in me an idea for arguing and debating the truth and figuring that out. And I think that one of my favorite definitions for genius is being able to retain the curiosity and wonder of a child into the power of well-informed adulthood. And I think that's really what he gave me. He gave me the, insatiable curiosity just to know how things work and how we can make them better. So next I'll talk about DOE and ORNL. I think I'm amongst friends here. I think many of you know what Oak Ridge National Laboratory does, but we have several world-leading facilities. As a computer scientist, a big thing that drew me was regularly having the world's fastest supercomputers. But we have over $1 billion a year that we use to fund over 7,000 employees currently. And we have some of the world's fastest supercomputers, largest spallation neutron source, a lot of unique equipment facilities. But what we really have is world-class researchers. We're worth the best and the brightest brains that we can find to help secure the energy future of our country. These are some of the capabilities that, if people ask, what does ORNL do? Well, these are many of the capabilities, and I put a red box around the ones that directly apply to the research that we do. Leveraging some of the high performance computing resources to take all this data and complexity and make it something really simple to use. That's really what it boils down to. Like Einstein said, you never really understand anything until you can explain it to anybody. So if people can't answer your questions, I don't think they really know what they're talking about. Most of my time at the last 15 years has been spent at the Building Technologies Research Integration Center, which has been around for 13 years. We have about 20 facilities kind of spread out around the campus. That allows us to deploy equipment, test equipment, measure how it performs under different environmental characteristics. And all this research allowed us to build new prototypes of equipment that is more, performs better than anything else that makes it into companies, develop innovative technologies, make it into informing incentives for local, state, and federal agencies for different technologies to improve market uptake, and then also on the codes and standards. The standards that I chair and basically defines the worst building you can build by law. Everybody wants a cheap home. So, we don't want it to be too expensive, but we want it to be energy efficient. So buildings built today use less than half the energy they did in 1995. But how can we do that and keep improving that so people don't have to pay the energy mortgage or have a high energy burden in their life while getting a cheap home or a commercial building? Be tricked by the numbers. So I like to say that the core capabilities is really the infrastructure and equipment and the people. I think all these other metrics follow that. So over 200 industry and university partners, over 130 publications, lots of R&D 100, 16 R&D 100 awards, 36 ASHRAE awards. We have 64 CRADAs, which is cooperative research and development agreements, where we're working interactively with companies. So we're not researchers out in left field. We're a very applied program that's working with companies and other organizations to put everything that we do into practice. And if you wanted to know about, if you had an idea or wanted to talk to someone specific, this is the go-to chart for buildings. So these are the sub-program managers that have a direct correlation with someone sitting in DC that makes the decisions on how they invest their money. And so we tend to have, 5 to 30 years of experience working with them, knowing what they're looking for, what they have. And then if you have a new idea, is it new? How does it apply? What are some of the challenges that it faces? So having these go-to people really makes effective use of all the ideas you can come up with and bundle them into something useful. And at the Department of Energy, a big thing that we focus on is stewardship of the nuclear stockpile and securing an energy future for our country. Specifically, most of my funding comes from the Department of Energy's Building Technologies Office. If you were to sum up your home's energy bill, all the commercial and residential buildings around the US, it's about $400 billion per year that we're paying for energy. I see that as a mortgage for our economy. I don't know about you, but I'd love to have $400 billion that I can spend on something more useful than just keeping the lights on. That's necessary, but how can we improve the performance of our buildings? So there's a little over 125 million buildings in the US. It's 40% of our total energy consumption goes into buildings. The total electricity, like coming off of the grid, 73% of electricity used by residential and commercial buildings during that critical hour of the peak calendar month, where they're spinning out all the cheapest and worst power plants. It's 80% of the energy use. So you can't solve the critical infrastructure, electricity, power without looking at buildings. It's one of the biggest chunks to look at. And so the Department of Energy's Building Technologies Office has the goal to turn the energy consumption per square foot or energy use intensity down 30% by 2030 compared to a 2010 baseline. So how do you reach into every home and office in the US and turn the energy use knob down a third in 20 years? That's pretty challenging. So what we do, what my group specifically does, is use building energy modeling, where we take descriptions of your building and the local weather conditions, and we run physics-based calculations to say, if you added this technology, a more efficient HVAC system, photovoltaics for your insulation, right? All these things that you can think of as retrofitting or improving your home, LED lighting, or efficient computing or appliances. We can quantify how much energy and money you're going to save with that. And then you can use that to make your decisions, right? What's the best bang for your buck in improving your building? So that's what we are typically doing with research and building energy modeling. Now I'm going to talk about some of the science. And a lot of people like to go directly into the science, but again, it's all a function of people. I'm the talking head today, but I want to thank the alphabet soup of a dozen different agencies that have funded this research and the small army of folks. Right? You don't see them here talking today. This is like the people that do all the real hard work, and I just get to talk about the outcomes of the proposals that we've had awarded. And some people like to dive into the science, but I like to start at the big picture. Why does this matter? Well, back in 2015, we set a big goal. I like to work on five-year visions. Right? If you have a group or people trying to do something, if you can set a goal marker 5 years out, then everybody kind of rows toward that goal. Right? It's not like herding cats. You're kind of working together toward a common goal. That's what makes friends, right? You have some activity that you do and they do, and in doing that together, you're closer together and become friends. So research is kind of the same way. So our goal was to create a digital twin, an energy model of every single US building. This is something that has traditionally been done one building at a time. It's taken a lot of time and money to create a single model of a single building, requiring architects, mechanical engineers, electrical engineers, all these kinds of people to make it happen. I wanted to upend the entire industry by using innovative data and algorithms. So In 2015, what was our roadmap? How do you create, if I asked you, how are you going to create a model of every single US building? Well, this is the roadmap of how you might want to do it. This is what we learned. So the first thing was, why do you want to do that in the first place? Why does it matter? Well, in the US, we don't have good data about buildings. There's a tax assessor's office that assesses an ad valorem tax to a parcel based on the value of that parcel in the building. They have some data. That data doesn't characterize the building well from how it works from an energy perspective. It's stored in different data formats. Sometimes it's just a PDF, and there's no simple fields. There's no unifying ontology where you could just take a union of all these databases. So we have no central database of US buildings. The UK is the only country I know that has such a thing. But if we could collect this data, then we could benchmark buildings. And with simulation, we could say, what's the best way to reduce the energy consumption, right? Reducing that 30% in 20 years. What do we need to do? What technologies do we need to invest in? What market uptake do we need? What technologies do we need these buildings in to achieve that goal? And then how much money what's the best way to invest that money to make that happen? So then you can reduce it, and for everything else, you need renewable assets to offset that for a completely sustainable building stock. So that's the three-step model to an energy secure and infrastructure of buildings. The way we did it, when we create an energy model of a building, it has over 3,000 inputs for a single building. Just like in life, you don't want to major in minors. You can, but it's not going to be a great life. You don't belong to have success and spend your whole life there. So what we did is we took a building and let's say the efficiency of the HVAC system. Here's the industry standard. And we're going to turn that up and down 30% and see how big a change that makes to the kilowatt hours consumed by that building. We didn't just do that for the HVAC efficiency. We got 3,000 knobs to turn, right? So we used design of experiments to turn all these knobs to quantify in terms of kilowatt hours and kilowatts, how big a difference does it make? We could not do that without some of the world's fastest supercomputers. This is a large sampling problem. And this combinatorial and dimensional complexity can bring the world's fastest supercomputers to its knees. So how do we do that intelligently? Once we find out what's most important, we start shopping around for data sets. One of the things that we like is satellite imagery. We can apply computer vision to satellite imagery and pick out the footprint of the building, right? So what are the data sets? What's the spatial resolution? What's the temporal resolution? How much does it cost? Are we going to get sued if we use it? What's the derivative IP rights? What's the API rate limits for grabbing this data and processing it, right? All these characteristics that you need to know in kind of a side-by-side data shopping process. Then we started creating partnerships with companies that are in the business of collecting or processing this data. And then we applied it at the scale of the entire nation, and everything broke. So we had to create new theoretical breakthroughs in artificial intelligence to speed it up. We had to find more efficient ways to deploy it on supercomputers to minimize the communication so that we could get the scale and performance we needed. And then we were able to achieve loading all the details. I was locked in a room once with 3 DOE and 3 UT Battelle lawyers, where I wanted to use some technologies that would allow me to see into buildings and gather information. And I was told quickly, you cannot do that if it's not national security. We're not Big Brother. We're not looking into your buildings. What we do is we look at the building and when it was constructed. And then based on that, we know if it was built to code, these are the properties of that building. So we're assuming it's built to code. If you have some fancy technology, if you're smelting aluminum in your building, if there's some unusual process, then our models would be off comparably. And then we made these models freely and openly available to anyone in the world so that they could use it for any simulation-informed use case. So in the last half of my presentation, I'll talk about how the businesses are using this. But to create a model of every building in the world, I would love to talk all day about the science. I could talk for years about it. I think it's so neat, the breakthroughs in artificial intelligence, some of the demos and walkthroughs we have. But at a 10,000 foot view, this is what we're looking at. On the left is the data sources. So we love processing imagery, satellite, aerial, street view, LIDAR, MLS databases, any kind of source or information about buildings. We love to ingest that data and use it in our models. On the right side are some of the software tools that we've developed for processing this data and turning it into something that we can use in an energy model. I'll skip over this in the interest of time. I was inspired by a quote that's often misattributed to Abraham Lincoln, who said, "If I had 5 minutes to chop down a tree, I'd spend 3 minutes sharpening my axe." Right? How can we do some preparation before that makes the process go quicker? And software, we talk a lot about scalability, which is how can we get software to do something so quick that we could not cut down one tree, but we could cut down a nation of trees, right? Metaphorically, what I'm saying is, how can we speed up the process of creating, simulating, and analyzing an energy model so that we can do it for one building so quick that we can do it for a lot of buildings within a tractable amount of time? So we worked with a utility where they wanted to look at all the buildings in their areas, over 135,000 buildings, and we were able to run 8 different technologies for every building in their territory and do that in 6.5 hours on a supercomputer. I'll show more about how that's of use to industry later, but I want to be thankful to all the supercomputers. We've used about 8 to 10, depending on how you count it, supercomputers across the country in this research. And specifically to Argonne's Theta supercomputer, we used over 100 million core hours in 2 years to process every building in the country twice. We use the energy model called Energy Plus, and that runs the physics-based calculations to tell you what the performance of the building is. And then the Open Studio is a higher level middleware that lets you easily run simulations in the cloud or swap out an HVAC system. But these are open source on GitHub, so you can see the source code yourself. It's free to use. And DOE has invested over $100 million since 1995 in the development of these tools. There's a 3,742 page input-output reference manual of everything you can put in or get out of this tool, courtesy of the American taxpayer and freely available. So that's what we use. In creating a model of every building, there's specific fields. So this is specifically the data, the 12 data fields that we're outputting. We did this in 2020, creating Model America version 1 that is public, freely available, and open source. We now have a Model America version 2. So in the red, I'm highlighting what's the differences between version 1 and version 2 for the digital twins of every U.S. building. Specifically, we went from 125.7 million buildings to 141.5 million in the U.S. and Puerto Rico. We do include Hawaii and Alaska in these buildings and these simulations. One of the challenges is we didn't have good characteristics of buildings, so we weren't for sure whether it was like a small office or a hotel. But in version 2, we solved that problem. We partnered with Google. You probably use Google Street View. They know where the Lowe's and Home Depots of the world are. So we mapped their descriptions of buildings into the DOE prototype buildings that we use for our simulations. Also, another thing is I told you we look at when it was built and assume it was built to code, and all the internal characteristics and operations of the equipment are based on that. But a lot of buildings are really old and have been renovated, right? So we had a partner in Lightbox technology where they knew where buildings under major renovations by pulling mechanical permits and other things from all of the counties across the country. So now we know when the building was majorly renovated, and we can update our building models to be more reflective of the building as it operates today. So the data is available at bit.ly/Model America 1. You can go look at it yourself and use it if you'd like. And then when you create a model of anything or a software model, you should never believe it, right? It's like doing calculations in a spreadsheet. Like you need to validate that your calculations are accurate. So in an unprecedented move for a utility, the Electric Power Board Chattanooga gave us 15-minute energy use from every single building in their territory. We had 186,000. We threw away some of it because it was kind of special, but we used 178,000 buildings worth of 15-minute energy use where we could run our model, compare it to the utility revenue meter data, and see what the difference is. And what that allowed us to do is evolve the data and the algorithms and the way we processed it to get closer and closer to the ground truth data. That's the power of the evolution of technology. When you develop a technology like that, it can change everything, it can change society. In terms of how accurate are the models, that's the number one question I get from scientists. So you built models, how accurate are they? Well, for Chattanooga, where we could get the 15-minute energy data, it's in green. And there's an industry, there's something called ASHRAE Guideline 14 that says if you can get your model to match real data within this percentage, that's investment grade, which means you can take the predicted savings to a bank and a third-party financier can sign off on it and get loan money to make changes in that building. So that's a big deal. That unlocks major investment. So that's the goals that we're looking for here in this last column. We'd like to be below for monthly data. This is monthly, hourly, and 15-minute. CV-RMSE calculated here, and normalized mean bias error calculated here. They both have to be below these percentages. So if you're looking at monthly data, you want to be below 15%. We were 2% error where we can get the utility data. In Chattanooga, where they just have self-reporting ordinances, we don't have real utility data, our median error rate was 30%. So not investment grade for most buildings, but for some. So that's the goal, is to get to investment grade models of every US building. That's what's driving my research direction. And I told you we were evolving the data and algorithms, right? So how good are those right now? Where we can't get utility bills, it's better than 93 out of 100 modelers. If you give this data to a human and they were to create a model, this software, completely automated, is better than all but the top 7% of them. If it has the utility data, it can do corrections and adaptations. It's better than 1 in 10,000 modelers. This software and its AI capabilities is superhuman at this point. We also have another capability where we want to look at what the impact of future weather is on buildings to make them more resilient against storms and power outages. And so there's different scenarios where you look at population, technology, and economic growth. We call those SSPs, and then RCPs, which is how much radiation is being captured. And when you combine those assumptions about technology and economic growth with environmental factors, you have a scenario that you can run. And so the challenge is that we have these global models that tell us the temperature and other meteorological variables that we expect out to, say, the year 2100, but they're pretty low resolution. And to get to building specific information, we really need to improve the resolution of that data. So what we did is we developed new capabilities via what's called dynamical downscaling, statistical, and then moving into artificial intelligence-based downscaling, where we can improve the resolution. The reason that's required is if you look at the planetary models, this is Seattle, and you can probably see, even if you're not familiar with Seattle, this gray region is where all the buildings are. These black points is where we have computed data from the models about what's happening near Seattle. So you've got something inland, you've got something in the mountains, you got something in the bay, you got something in the ocean. Nothing about what's going on where the buildings of Seattle are, right? So that's why we need to downscale to a higher resolution. We typically have 50 kilometer to 100 kilometer grid points in that data, but we've gotten it down to 4 kilometer daily data via LibNet and DayMet downscaling algorithms. And then we had to develop, that's kind of a common algorithm. we developed new algorithms that allowed us to get down to specific GPS points of interest, any point of interest, to hourly data. We need hourly weather data for building energy models. What we did is we took this is a cross-pollination of science. So we took our data set of all the US buildings, and for every US county, we said, where's the biggest cluster of buildings? This is the biggest cluster of buildings. Here's the GPS coordinates. And then we downscaled all those models to those points for every US county. Now we have US county specific weather data for all the different scenarios. There's a standard method. There's a standard method where we take like historical weather data and we say, okay, what does the weather in Knoxville look like in a typical year? We call that a typical meteorological year. There's already a standard process where we've overanalyzed this way too much. And we say, okay, given a 20-year period, we can give you an hourly weather file of what the typical weather is in this region of interest. Well, we applied the same technique, but to simulated data. So this is an example. You can take, this is each row is a year, and each column is a month of weather data. And then applying this technique, it allows you to select a representative January, in this case from 2011, a February from 2018. You just copy and paste those months together, stitch them together like Frankenstein to create the Frankenstein weather file that shows you what the typical weather is in that historical period. We do the exact same thing, but we do it for the future based on the simulated weather pattern. And the thing is, we actually use several different models. So some models have strengths and weaknesses, and oftentimes you want to solve a problem multiple ways and see if you converge at the same answer, right? So we take into account multiple years, multiple models, and apply that same technique as like one technique to rule them all in Lord of the Rings language, and create these weather files. The weather files are now freely available at bit.ly/FTMY for a future typical meteorological year. It has weather data for every US county and the 18 cities that we use for building codes from the years 1980 to 2100. So if you want hourly weather data from 9 meteorological variables, 1980 to 2100, it's freely available online. We've had over 6,000 downloads in the first few months of this data. And this is kind of a reference. I don't know if any people are interested in digging in, but if you want the code, if you want the data, if you want the standard methodology, if you want to just look at the visualizations of it, all those links are here. Now I'm going to get into what I consider the most important. So what, all that science? How do people make money? Right? What are the business uses for this data? Well, I will say that there's different industries that we focus on. I personally like to prioritize everything. Maybe it's a character flaw of mine, but I want to know, how big is your market size? I could spend my whole life servicing a $50 million industry, or I could service a $500 billion industry. I think I'd make more over there, right? So I'm trying to find out what's the most important problems. There's utility programs. Everybody has a local power company, right? You pay an electric bill and natural gas bill. These people have energy efficiency and demand response programs where they're trying to make sure they're operating their infrastructure correctly, and they're improving critically loaded feeders and substations so they don't have to put more transformers and other things in the infrastructure just to keep your lights on, right? So together, that's about $11 billion per year across all the power companies in the US. There's also something called energy service companies, which I'll get into later. It's a very interesting business model, which I hope can apply to more buildings in the future. But I've had a lot of CEOs come to me and said, we've got a lot of money we want to invest. Let's say we came to Anderson County, and I want to put $4 billion into improving buildings, but I want to make $10 billion in 15 years. What technologies do I need to put in what buildings? What doors do I need to knock on and sell a program so that I can make my money back and a profit within a certain time period, right? So our technology can help answer those questions because energy models can quantify the energy demand and cost savings for pretty much any technology you can think of that can be deployed on a building. So first, business use, summary of business uses. This is the breakdown of what I see as the total market value of each of the different areas that I'm going to talk about. So hardware and home improvement stores, people selling windows, doors, HVAC systems, and insulation. How much money could that save you? The total in the US is about $328 billion. That's that's most of the homes and Home Depots and Lowe's in the world. Architectural and engineering construction firms, right? We build about 1 million buildings every year in the US. And there's all these architects and engineering firms that go into designing commercial buildings, right? A lot of people that want to make the next Sydney Opera House for the US. Utilities, already talked about with their efficiency and demand response programs. Energy service companies is a $30 billion a year market. Commercial and real estate lenders, it takes money to create and own commercial real estate. And there's people that loan this. They want to know what weather is going to do that erodes their value and their ability of their commercial building owners to pay their leases. Cities are kind of tasked with making their city run energy efficiently, being performance aware. And so across all the cities, the energy use of buildings and cities is about 270 billion. The government spends about 16 billion specifically for reducing the cost of federal buildings. I'll talk a little bit about some of the programs that are going on, but with a lot of the, leaning up of the government, they want to know how they can do more with less, right? So how can we be compliant with some of the requirements while spending less to do it? And then some of the future capabilities, resilience. If you want to know how buildings are going to be impacted under extreme weather events, insurance is involved. It's a $9.3 trillion industry. There's a lot of interest going into the new games and models and data to see how buildings are going to be impacted and how we can prepare for that, reduce the back end costs. And then I'll talk a little bit about automated financing. Are there ways that we can use innovative data sets and tools like this to grow the retrofit rate of buildings, and that moves from single digit billions to hundreds of billions of dollars of improvements across our nation. So I mentioned let me pick someone out of the audience. Can someone stand up and tell me your name? I'm going to pick a victim if you don't participate. I'll ask you, what's your name? Roger. Okay. Let's say you own a store where you sell windows. Okay. So tell me a little bit about your window. Why is it so great?
It's triple paned and it shuts out the ultraviolet images, fabrics and other things inside your window.
That's
insulated. Things don't degrade like some do.
I think he really owns this store, don't you? All right. So I'm a savvy customer. So what's the solar heat gain coefficient and U value of that window? Okay. So see, I'm kind of losing faith in this guy now. Now, how much money is that going to save me? I mean, I pay, on average, $1,800 a year on my energy bill. How much is that going to save me?
Savings 5 years.
5 years, simple payback. Okay. I wasn't sure. He gave me some numbers though. But how do I know his numbers are right? I'm kind of skeptical because I know he just wants to sell me something, right? But what we can do is the Department of Energy or these tools could be used to run a third-party assessment of your window, right? You could put the characteristics of your window in, and if they're accurate, we could run it in our models and say, not just for a typical home light, but your home, your specific home, where it's at, what weather it gets, the shape of it, how many windows you have, how much money will I save, right? If you tell me you can save me a lot of money and I can pay it back in 3 years, not just because you said so, but because the Department of Energy says so, I might do that. Right? So what we have now is a tool where you can in live update the digital twin of the model. You can see here people put in their street address, and we'll zoom in on your building. We'll load all our data from our database about that building. If our footprint isn't right, you can adjust it. Oh, I added a wing to the building. You can update the characteristics of the building. And then we can give you, if I can get the mouse over here to click, we can give you a breakdown. Here's your building before the technology, and here's your building after the technology. How much less heating, how much less cooling, how much less electricity, how much less natural gas, how much less fans do you need to use? All of that breakdown. And here we're showing a 6-year payback. So his estimate of 5 years wasn't too bad, right? Most people only own their residential home 6.5 years. So getting a payback period below 3.5 to 4 years that an average homeowner is in their home, that's pretty challenging, right? But now we can quantify it not just for any home, but for your home for a specific technology, and have a third-party science-driven and all the reports and data you want behind it that tells you whether this is a good investment or not. I'm hoping that will stimulate companies and uptake of some of these technologies. Another thing that we do is architectural and engineering firms that design buildings. Right now, architects want something that looks pretty. Every building is all glass. Everybody loves glass. A wall doesn't let as much heat in it. A window lets 10 times more heat in and out than an average wall. So while windows look pretty, they're not a good energy efficiency technology. Maybe one day we'll have walls and we'll have displays that are so cheap, we'll have a high-def rendering of the outside as like a display on the wall. That might be more energy efficient than what we got today. But the problem is architects are designing these buildings and they don't have feedback on what the energy impacts of their design decisions. So typically, this is the process. So they know that they're going to build a building in this location, right? In this square, whatever. This is the parcel. And they know that it's in this climate zone. It's going to be this building type. So we've got these building codes that we have to meet as kind of the worst, cheapest building we can build by law. And then there's this thing called the energy use intensity target, the energy consumption per square foot, which is defined by the customer. If I don't care about energy, just give me a cheap building. If I don't want to pay too much in the back end with all the operating expenses for energy, I'll reduce that target, and it's almost always reduced. But now you got these architects that are in the blind, kind of designing a building, and then later on in the design phase, when they're ready to start constructing it, they're like, whoops, we can't do that because it doesn't meet the energy targets. Well, what we did is we flipped that on its head. So now you've got this parcel, you've got this building you're going to build, and you say, this is my energy target. And then we put bumpers on the design space that says, you want an all glass building, but you can't get but 50% glass with some of the best technologies, and it's going to be expensive, right? So the way we did that is we looked at all these different types of buildings that this company builds, all the different climate zones in the US, and then all the different characteristics, like how much light do you want coming in from the sun? How good do you want the building envelope to be in terms of insulating against the outdoors? How advanced do you want the lighting to be? Do you want it to be typical fluorescent, or do you want it to be LED? And we have all these different options, and because we have supercomputers, we can run every single combination. And that's what we did. So we know all the trade-offs. This is like a hot-cold map that says, if you want really efficient buildings, select the blue. These red buildings are the worst. That's the combinations that don't get you where you want to go. And then we fed that to artificial intelligence. So when you look at the simulated from the physics calculation, and then the AI estimated, it's an R squared of 1.0. So most of the scientists in the room, that's really good, right? AI is nailing the prediction of energy use. The good thing is physics simulations take 20 seconds to 5 minutes, depending on the complexity of the building to run. AI can do it in milliseconds, sometimes microseconds. You're talking about real-time feedback. As a building designer is constructing the building, they're getting real-time feedback on what the energy impacts are. So this is from a company called Smith Group that we partnered with. Understanding is there is about 20 architects that are currently using this prototype tool. You'll see as they change things on the left side, designing the building, pulling all the levers and knobs to construct a new building. You're seeing the 3D model update live as they're selecting it. But in the top left, you have an estimate of the energy use intensity. So every time they make a change, they're saying, oh, is this moving me closer or further away from my target, and by how much? The cheapest way to save energy is in the early design phase of a building. We had no tools to look at the energy impacts. Now we do. We can also guide our architects and designers. So if you look here, I'm going to pause the video. We're looking at a building that uses 72 kBTU per square foot. These are all the other mass simulated buildings that they could design. That's not a good design, right? How do you drive down the energy use? And through making a few changes, they drive that dot all the way down here to 38 kBTU per square foot. They cut the energy use of the building in half just by changing a few options in the early design phase. So this is being used to inform the design of buildings. And I've joked that if we recorded data and we saw how the architects use this tool, we could replace them with artificial intelligence by just turning the knobs the same way they do. So I don't know if we'll get there, but it's certainly a technology to look at. So if you were to pay a person to create an energy model of a building, they usually get paid about $150 an hour. Pretty good job. It takes them about a week, 40 person hours to create a functional model of the building. That's $6,000 to create a single model. With our technology, we can simulate over 1 million buildings in a single hour. That's a force multiplier because that's $6.4 billion worth of work that would take someone over 20,000 years to do, and we can do it in a single hour. So this kind of technology is not just, it's a force multiplier to an entire industry. Another thing that we look at is utilities. I talked a lot about the Electric Power Board of Chattanooga, which was a key partner. And they specifically wanted to look at these options on how to reduce their operational costs for running their distribution network, the power lines and all the things that go into getting the power to your home and keeping the lights on. Well, technology is speeding up. So many things are speeding up. If you look at how long it took for the telephone to be adopted, or stoves and refrigerators, I mean, look at the internet and the cell phone. It went from 0 to nearly 100% penetration within 5 years. Technology is adapting and moving fast, and it changes the entire landscape. A single technology changes not just an area, it changes us. As an example, this is the paper pong play from 2005. You see two people on cell phones. This guy has some blue light on his face. He might be using a cell phone. He's got 3 cell phones there. What do you think happens if I fast forward from 2005 by 8 years? Okay, it's changed us. It's not just how we interact with the world, it's changing the way our brains wired. Our units of information that we used to know is 7 plus or minus 2, now it's 3. We don't have working memory that we used to. But technology's here, whether you like it or not. It's a double-edged sword. It is good and it is bad. So how do we use that? Well, EPB has all these substations and feeders and buildings in their territory, and they want to know for like critically loaded lines, they've got to put a higher capacity line, they got to put a new substation, they got to put new transformers, or they're going to have to reduce the load in that area somehow. If they can defer that infrastructure upgrade, that makes them operate more efficiently and makes them not have to raise their rates for all the people paying their utility bills, right? So the good, the bad, and the ugly. The good is we had GPS coordinates for every single meter, and we could map our buildings to the individual buildings. They also had characteristics. So is this a commercial building? Is it a residential building? They pay different ways, different rates. We could map that to our building types and say, you know, are we having a good one-to-one comparison? One of the challenges is our data is always old. By the time you process it, there's new data. And in this case, they had built an entire new subdivision by the time we finished processing the data. So we can help almost all the buildings, but the newest buildings are not in our data. Another challenge is this is the ugly. So we like processing imagery, street level imagery, right? I can count how many windows are facing the street with computer vision algorithms. And if you look at this image, it's the same building, right? This tree is in front of the windows here, but not in front of the windows here. Same views, different angles, right? And you can see it's a 28% window to wall ratio versus a 30%. So you kind of have to average over multiple views, right? Another challenge is that some buildings have a lot of things between them and the road, so we can't get a clear picture of them. They're really far away from the road, so we can't see anything at all. There's just not enough data. And we can actually see on the backside, like if we go around a block, we know the GPS coordinates and the angle of the camera, and we can get some of the back information. There's also some details like picking out the number of HVAC units. We've all probably driven by a building and seen all the rooftop units on top, right? How many of them are there? What size are they? It's the kind of thing we'd like to count. Specifically, there were some technologies that the utility was interested in looking at. So they just said, like, if we could bring all our buildings up to current code. The way code works is every 4 years we release new building codes. But every state elects what year of code they're going to enforce. So even though we're in 2025, the state of Tennessee, I think, unless they've updated, is enforcing the 2012 building codes. We're like a decade behind. So they just said, what if we brought like the 1980s buildings up to 2012 building codes? Well, this is the definition of that, moving from R16 to R29 in insulation levels, right? All the numbers that we need. And we found that they could save $11 to $35 million a year in their territory. In each of these scenarios where we break down the total savings and the amount per building that they could save, and we have a full report of how they can implement this to realize those savings. Well, one of the outcomes of this is they introduce that data into the dashboards that are used to make operational decisions on their distribution network. So it's too much data for a human to look at, but now they have a dashboard where they can say, just show me like the single story buildings. Show me just the residential buildings. They can filter this data. They have a map that shows where these buildings are. They have charts that show how much they can save. As an example, a utility, there's something called smart thermostats now. Right? You can talk to your thermostat and set the temperature in your home. What if a utility could send a signal and say, hey, it's going to get really hot and people are using a lot of energy. Can you cool your building now rather than when everybody else is? And if they can send that signal to your thermostat, you can use your building as a thermal battery, precondition your building, coast through the hour of critical generation, and now the utility is saving money. They give some of that money to you for participating, and everybody makes money. Well, this is one of the examples where they were looking at having a smart thermostat where they say precondition it by 4 degrees Fahrenheit. If you're having a party, if you're uncomfortable, you can always override. You know, customers always right. But if you allow us to send that signal, they found that they could save over $3 million in their territory by deploying smart thermostats. And in fact, if they paid $375 for a thermostat and installed it for you, they would still make money. If they kept only 40% of the savings and gave you 60%. So would you like a free smart thermostat and save money? I think this is pretty simple. I think all utilities should be doing this kind of thing. They also looked at ways to improve or make HVAC systems more energy efficient. Utilities should be tuning up their HVAC systems. It's in their business interest. There's all kinds of other improvements to buildings that it might be effective for utility to do and save us energy. So one of the takeaways for this is Tennessee Valley Authority produces electricity in our territory. Our local power company buys the energy from TVA and sells us the energy. And the delta between that wholesale and retail rate is how they make the money to own and operate all the power lines and everything that has to go into it, right? So with this technology, TVA raised their rates 3 times because energy gets more expensive, right? Inflation and everything else. EPB kept their rate completely flat. So every homeowner, every business owner was paying the same bills that they had 3 years running, while TVA's rates and everybody around them is increasing. I thought that was a huge success story, right? If I could go to another local power company and say, can you give us your building data? We'll make you not have to raise your rates for multiple years. I thought most utilities would be very interested in that. The truth is, most utilities are very conservative. Providing utility data to anybody, even the national lab that protects the nation's nuclear secrets, is not something they like to do. So it's not been as successful. And the reason, one of the reasons I created a model of every US building is because I got tired of asking utilities for their data. If I can get sufficiently accurate with my simulation, I can have a pretty good surrogate to your energy data. I don't need the utility bill. So we have something called bit.ly/virtual_EPB. I won't go into the live demo model, but you can go to this website and you can color code buildings. So if I had a smart thermostat program, you can zoom in on the buildings that have the highest potential, click on it, and it breaks down. You can't see it probably too well, but every row is a technology. And this is the column of energy savings in terms of kilowatt hours, demand in terms of kilowatts, and the total annual dollar savings. At the bottom, we say the combined package of these technologies can save you this much. So this building cuts its energy demand by 49% and saves $236,000 a year if it were to do those 4 things to the building, right? I would love to save $230,000 in this case on a commercial building. Another use is commercial real estate. So it's a $580 billion a year industry, pretty big. And laid this a little bit earlier, but let's say you're a commercial building owner. I'm a bank and I loan you the money, like build the commercial building and own it. Well, now you got to pay the energy bills for your tenants to operate their business in that commercial building, and you're paying a commercial lease. I, as the bank, want to know, when you pay your energy, how much money are you going to have left to pay me, right? If energy bills are going up, if energy costs are going up, if the climate in your hot area is getting even hotter, that's going to erode your ability to pay me back, right? It's a risk to me. So they want to know how that operational expense is going to change. And so we worked with Lightbox, where we can quantify by the year 2100, under a 5-degree Fahrenheit increase is what we're estimating. You're going to have 16% more electricity use and 23% more demand in the area of Phoenix, Arizona. So we did this for a lot of different areas, and now it's being used by Lightbox, who services 54,000 commercial real estate lenders. So this is a pretty big fraction of the $500 billion industry that's already leveraging this technology. The next one is cities and software developers. If you look at the number of buildings in cities, the total energy use of buildings in cities is about $270 billion per year. So how can we reduce that? How can we make more energy productive cities? We typically work with people that can't simulate hundreds of thousands to millions of buildings, and if they don't want to pay us to do it, we're glad to provide them less than 100 models, where instead of 10,000 supermarkets, we know what the typical supermarket is, and we have a floor area multiplier. So run one simulation instead of 10,000 and multiply up the total effect if you put that in all the supermarkets. Well, the error rate you introduce with that is about 7%, but if that's good enough for your business decision, Then with 10,000 less compute, instead of a supercomputer on the laptop, you can run your own analysis. We work with Google. They have a program, a system that does this. If you Google Environmental Insights Explorer, they show the total energy use for a city broken down by buildings, by transportation, and how much photovoltaics would allow you to generate in this area. Well, they had their own method for estimating the energy consumption of buildings, and their average error rate, they had 8 cities that gave them the real utility bills for all the buildings in aggregate for that city. The average error rate for the prediction algorithm was 35%. Not too good. Our average error rate, when we looked at that, this is the AutoBIM line here. Average error rate was 2.3%. I know it says 3.5 here, that's a typo. 2.3%. The worst case was Washington, D.C. We were off by 5%. That's pretty good. I mean, if I had a big portfolio of buildings in a city and I could be off by 5%, I'd be throwing money because I know pretty tightly how much I could stand the winner lose. Another one is in the government. So the government is tasked with reducing the energy cost of all federal buildings. Specifically, there's something called the Energy Independence and Security Act, Section 432, that says 25% of buildings that meet certain criteria have to be evaluated, and you have to tell us what technologies would save you how much every year for 25% of your buildings. Well, there's been a lot of cuts in the government. Right? We want to operate more efficiently. Well, if we're cutting people, maybe we need to add AI technology to make up those shortcomings. What if instead of paying people to walk through buildings and do these calculations, we have a technology that already has every building in the U.S., just pick out the federal buildings and do that assessment? Does that check the box on what's required for ESA compliance? Also, to make those improvements, there's this question of how much money do we need to set aside to improve these buildings? Which technologies would be the best investment? How much money do you need? Right? All these financing questions can be informed by this because we not only know how much those technologies can save, we know how much the equipment costs and how much it takes to install in the local area. So now we can do a full ROI calculation with all kinds of techno-economic metrics to suit your interest of what the best investments are. And close to the final slide now, the future. What does the future look like? I think that we're going to face a lot of challenges. We always do. Economy, environment, businesses, disruption of technology. How do we make buildings prepared for what is to come? Now we can run all kinds of scenarios. Maybe we can't do every scenario. I can't. But if you can define, what you want to look at, I can usually generate a weather file or a set of buildings. We actually have AI that can evolve cities. So like how are cities going to get taller and grow and sprawl and densification, all these fancy scientific terms. And we can kind of play forward time and see how our cities evolve. We can run all kinds of scenarios to say, under this situation at this time period, what's going to be the total impact? And we can figure out what are the best measures or countermeasures to mitigate those effects. As I said, this is of interest to insurance, right? As an insurance company, if I can invest $1 million to reduce a $1 billion risk 20 years from now, I'm going to do that. Right? It's just the way business works. So how can we improve the models and reduce the risk and uncertainty for scenarios of interest? And then finally, what I'm really interested in is what I call automated financing. So in the US, we improve about 0.3% of our 141 million buildings every year. 0.3% is a very low number. We'd love to see that above 1%. I'd love to see that even more. But there's something that's kind of interesting. There's something called PACE financing. I told you it's challenging to get something that pays itself back in 3 years. 15 years is pretty good. But there's a program called PACE that says you can retrofit a building And what we're going to do is we're going to add the cost of that retrofit to the tax burden for that building so that you amortize that cost over all the building owners. Now, a building for the next 30 years can be much better operating because everybody's sharing the cost of that retrofit. There's standard forms, there's standard analysis, there's standard methodologies, figuring out which technologies you should apply to PACE financing. The problem is that for local codes and because of legalese, right, there's certain easement rights and all these other things, the paperwork has to be specific to the local area. But if I could get that, I could potentially automatically generate the paperwork necessary for a third-party financier to sign the document that authorizes multi-billion-dollar loans for a company to make the changes in the buildings and secure the equipment to improve the building performance. So I think that will expand from what's roughly a $6 billion industry. Easily, there's reports out there that show at least $133 billion in the US. Now, if I could give you a free upgrade to your building with new equipment that feels better, that operates better, at no cost to you, and I can make my money out of the energy savings in the back over a 17 to 30 year period, would you do that? If you pay $1 million a year in energy bills and I'm asking $700,000 a year for 17 years, you're making $200,000 a year. You've increased the resale value of your home or business, right? It's a very easy win-win decision. And I'm trying to get to the point where we can make sure our algorithms and data is accurate enough and can automatically generate the paperwork to make that happen. So, final slide. Thank you guys for sticking with me. We use some of the world's fastest supercomputers to simulate every building in America. We can make this available to any set of buildings. Like if Starbucks came to me and said, here's all the GPS coordinates or addresses of our Starbucks, but we want one model of a Starbucks. And we want to know what we can do to all our chain stores to improve the energy efficiency. I could get them one model. If you say I'm a utility and I have this region of buildings and I want 50 models, I can tell you what the accuracy trade-off is going to be and the models that you need to run any kind of the thousands of improvements that you can make to a building. We also have future weather data freely and openly available along with those models. It's being used by architectural firms. It's being used by utilities to make distribution decisions. It's used by Lightbox, which services 54,000 commercial real estate lenders. And it's being used by Google to improve 40,000 cities nationally and internationally in energy use of buildings. And with that, I'll be glad to stop and take any questions. Yes.
Did you include in your buildings like rural areas, like mobile homes and farms and things that you might not be able to see
Right.
From a vehicle?
Right. We typically look from satellite imagery, and we're really good at getting through tree cover now. So unless it's very unusual, we probably have a model of every mobile home and every barn. That having been said, we know when the barn was constructed and we kind of assume it has HVAC equipment. So if it's not a conditioned barn, then our estimates would be off. Mobile homes are also very different from a traditional home. There are two government agencies that are interested in improving our models for mobile homes so that we can include it as a building type in our software, but that's not done yet. So barns and mobile homes are not supported right now. Yes.
You kind of glossed over how much electrical and gas consumption data you really had to work with. And there's privacy questions about that real time.
Yeah, so those are good questions. I can answer some of it. Ask me, follow up if I'm not answering your question. We do, so calibrates in this field means that you have these 3,000 inputs. So you're going to change the input so that the simulation outputs the data that's really close to the measured. The problem is It's an overdetermined problem. I can set these knobs to define 4 billion different buildings that are within 1% of the measured data, but they look nothing like each other. Right? So your estimates are completely off depending on which model you select. We use that as a post bias adjustment, which means if we run our model and we say this is the energy use and you give us the utility data and we're 10% over. Yeah.
You gotta move them, then we examine them, like our numbers up.
Yeah. So
You can't get the numbers out. Correct.
let me get to that. So if we're 10% over, we'll reduce all our predictions by 10% to get it to match the measured data roughly. For the stuff that I showed today, there were two main sets of data of utility data we used. 15-minute energy use from 178,000 buildings in Chattanooga, Tennessee. No, individual buildings with the unique GPS coordinates of the electrical meter outside the buildings. And what that allowed us to do is to improve our data and algorithms to where we can match that data. Now, the trade-off in privacy is we're a national lab, protect the nation's nuclear secrets. It's not like a company where we're using or selling that data elsewhere. It was under strict controls, guidelines, certifications, and unless EPB personally approved it, then I would not be using or looking at that data. No one else had access to our secure server for that. The other thing was that we were doing research from 2015 to 2020, and this data was from 2015. It was kind of like an old snapshot, like potentially 5 years ago of the utility data. The second data set we used was the aggregated energy use of buildings from 8 different cities that Google was able to attain. And their average error rate was 2.3%. In aggregate, it avoids some of those privacy concerns. But obviously, if you have the GPS coordinates of the meter and unique detailed information, there's a lot of things that you could back out of that data that could raise privacy concerns. So there was,
Yes.
they were just an electrical distributor, so we only knew electricity. For Chattanooga, we did not have natural gas data. Right. That most buildings in the Southeast use a natural gas furnace. So from the electrical load, we could tell they're using natural gas for heating. Otherwise, the cold months would have a huge increase in electricity. Does that answer your questions? Okay.
Yeah, I wanted you to talk a little bit about just some energy saving technologies. I know they're doing some on-site 3D printing of buildings. At least from what I know from making parts, they could print the building on site with insulation issues, even put the rebar in there by 3D printing. And I know it's such a big issue now. In California, they're building 2.7 buildings or residential per 100,000. In Houston, it's over 7. And even though the technology is there, people want to live in the San Francisco Bay Area, they're moving to Houston because they can't afford a home. And also just comments on, I didn't realize until recently, this New York Times article, 2023, 440 gigawatts have been solar have been installed in the world in 1 year. Nations like Pakistan, 30% of their energy generation in less than 1 year, because the cost is getting so low for this kind of thing. And geothermal, which is really applicable to such a small area of the country, now they're using some of the technology they picked up from fracking for oil generation that makes it applicable to a third of the United States or more.
Yeah.
How much, and then they have solar shingles, they have solar paint.
Yeah.
I mean, how are these going to play into the future that makes the plant many of the things that we now are thinking in our current model?
Yeah, that's a great question. The truth is nobody knows, but I can answer that on several fronts. So one is there are tried and true technologies today that we know you apply it to your home, we can quantify how much energy savings you're going to have. Let me break it down for a homeowner. Okay. There's lists. If you're a homeowner in this area, you should do these things to your building. One thing that people ask a lot is adding insulation, right? We condition the inside. We don't want it all going outside, because then we got to put more on the inside, right? It costs money. The thing that you want to do before that is actually seal your ducts. So your HVAC unit conditions the air and pumps it in through the registers in the room to blow the hot or cold air, right? Average uninspected duct is 14% leaky. The HVAC system on average across the US is 54% of the home energy use. So on average, we're spending 7% of all our energy to heat and cool the outdoors. So that's the first thing you want to do. Also lighting. LED uses 1/9 of the energy of an incandescent bulb. That's an easy thing. Oftentimes with these contracts, we're trying to make everything pay for itself. And lighting is one of those cheap and easy technologies that can make a lot of savings where you can add some deeper retrofits and still be cost effective. If people improve their lighting and their HVAC ducts and added insulation, there's not much more you can do cost effective as a package. When it comes to photovoltaics, it's increasing in deployment. The problem is we need energy when the sun doesn't shine. And so batteries and storage is the number one problem. There's a lot of effort going into how do we store this energy. In fact, in California, even in the US, they produce so much energy from solar, they'll pay you to use energy. It's like the grid is full. We can't handle this anymore. We need to dump it. We'll pay you to take energy at this time, right? The problem is everybody comes home at 7 p.m. You got this new peak because everybody's turning on their HVAC systems when they come home. So there's the complexity by which the systems interact makes a lot of technological challenges and business opportunities. When it comes to like photovoltaic paint and windows and other things, those are all technologies that are kind of cutting edge right now. And many times they're not cost effective, sometimes they are. But you always need to push those technologies because if costs keep coming down, then they'll be the new thing, right? So like photovoltaics, when it first came out, kind of a niche thing, nobody cared. And now it's so cheap that it's cost effective to deploy it and make money.
There is a chat question that's interesting from Robert Kennedy. He says, I am also concerned about the potential misuse of this powerful tool by predatory lenders or private equity real estate speculators. How do you feel about that?
This is one of those things that I'm going to generalize this. So beyond my tool, technology is always a double-edged sword. Oak Ridge National Lab was founded creating the bomb that ended World War II. Right? We've created nuclear power. We now get energy from that technology. We have safeguards and controls and non-proliferation programs to make sure that not everybody can build the bomb to hurt other people. Right? It's always a double-edged sword. So I think that every time you develop a new technology, scientists and engineers are often very short-sighted. They're just wondering, can we do it? As I joked earlier, like a scientist can tell you how to build a dinosaur. A humanitarian might tell you why that's not a good idea. Right? There should be safeguards, there should be controls, there should be practices, anonymization, all these things that go into how this technology is deployed to safeguard people from people that just want to make a buck. At the same time, people make bucks by offering products and services that people want. So there's always this balancing act.
We talked about economic incentives to improve energy efficiency in buildings. One challenge that I see around here, and I think is common around this country, due to residential energy use, is that there seems to be no mechanism to get privately owned commercial rental real estate upgraded, that it's, when the tenant is paying the utility bill, the landlord is not interested in any incentives to upgrade the energy status of the building. The tenant may not have the resources to do the renovation on their own. And even nonprofits and utilities provide support for homeowners to improve their energy status, but not for renters. So we have a situation where there are people spending hundreds of dollars a month for energy on a really tiny house.
Yeah.
And has anybody worked out that incentive process among the businesses you've interacted with?
The short answer, not that I've seen.
Okay.
Maybe there's a creative solution I haven't heard of, but we call that the split incentive problem, where you have like a building owner and a renter. The renter is tired of the energy costs, but the building owner doesn't want to pay to improve the energy efficiency because that's just money out of his pocket. He wants rent. He don't want to pay more, right? So there's this tension. Now, a good landowner will say, "Oh, the tenant's complaining. They want to improve the energy efficiency. If they do things that make sense, then I'll knock that off their rent because I know that that building is going to have a higher resale value, right?" So it takes some intelligence, and many landowners or business processes, they're not built to be intelligent. They're built to just keep the wheel running and keep the meter spinning, keep the tenant in the building, and doesn't look at those opportunities. One of the things that I've seen is when I talked about energy service companies where they can put new equipment in a building, so that you have a new equipment, better operating building, more comfortable, higher resale value up front, and they make money out of the energy savings on the back end. That is only for large commercial buildings today. Commercial buildings below 50,000 square feet and residential, completely unserved. That's a market. The problem is, how do you roll a truck? How do you implement something in a residential building so that you make enough money to pay off the equipment and make a profit? This technology can tell you what to do, but you still got to find out how to do it cost effectively. If you can do that, there's hundreds of billions of dollars to be made.
How often is the information on cost of devices that accomplish this energy savings update? Because parents might be important.
Yeah. So there's the thing is we have like 6 databases of information that tell how much different technologies cost in different areas for the equipment, for the labor, and then the maintenance cost on the back end to maintain them. That is highly variable by region. It is never up to date. So what we do is we say, this is our best guess. But when we work with a company, they say, I know what's in that building. I know how much this costs to maintain. And we just update our data algorithms, and then we kick out a new report that uses the correct data.
It's like, they have a lot of thermal mass. The house, changing slowly. Little contribute that's no one understands what you think about here. What in your building material that has the most thermal mass?
Well, I like libraries because they have a lot of books and that has a lot of thermal mass. That's one problem with simulations in general is they move too quickly, and we know that they don't move that quickly in reality. And generally, anything that has mass that accepts heat has thermal mass.
I love what has the most thermal mass. But
Because it can store a lot. It doesn't have a refract. Yeah,
water has the most mass.
it doesn't have a high albedo, which like aluminum doesn't store it.
The heat goes in and out very slowly.
Yeah.
And so that's what really has thermal mass until it shows it all together.
For sure. But everything that like these chairs have thermal mass, right? We humans, we eat food, we spew out heat and moisture. We have to take that into account in our calculations because otherwise they'd be very off. But thank you for the questions.
If there are any more questions, you can come up and talk to them later. I think it's come up. Talk and appreciation for you and your talk.
More caffeine.
Yeah.
Thank you. Thank you.